For decades, the recipe for making a better computer was simple. Take a transistor and make it smaller. By packing more of these tiny switches onto a single silicon chip, machines naturally became faster. But that strategy is colliding with a hard physical limit. Today, we are engineering microchip components so small that they are measured in individual atoms. When you shrink parts to this scale, you hit a barrier known as quantum tunneling. In a classical computer, a transistor acts like a gate to stop the flow of electrons. But at the atomic level, those gates are now so thin that an electron can simply teleport right through them. If an electron can bypass the physical barrier, the basic mechanism of the computer, the binary switch that reads as either open or closed, becomes unreliable. Solving the next generation of complex problems is impossible if we just try to build a faster version of the same machine. We need a computer that operates on an entirely different set of physical laws. That new architecture replaces the standard unit of data, the bit, with the quantum bit, or qubit. A classical bit is a rigid switch. It is locked into an absolute state of either a 1 or a 0 at any given moment. Qubits function differently because of a property called superposition. Superposition allows a qubit to exist in a state of probability. It acts as a 1 and a 0 simultaneously until it is physically measured. This probability state allows the computer to hold and process multiple pieces of information within the exact same physical space. By moving beyond the binary switch, we change how data is processed. Instead of finishing one step before starting the next, a quantum machine uses its multidimensional space to work through complex variables at the same time. In a traditional computer, adding 1 unit of hardware gives you exactly 1 more unit of power. Quantum architecture scales explosively. This happens through a second property known as entanglement. When you entangle multiple qubits, they share the same quantum state. This means the total processing power of the system multiplies exponentially with every qubit you add. Think of a maze. A classical computer tests one route at a time, hitting dead ends and retreating. A quantum computer approaches as a wave, evaluating all routes simultaneously, instantly illuminating the direct path to the center. Quantum advantage is not about moving faster down a single road. It's the ability to see the entire map at once, finding the optimal solution. If this architecture is so powerful, why aren't we using it for our daily electronics? The challenge is a phenomenon called decoherence. Decoherence is the collapse of a delicate quantum state back into a rigid 1 or 0. It is triggered by the slightest outside interference, like heat, stray atoms, or magnetic waves. To prevent this collapse, quantum processors require extreme isolation. They're built inside dilution refrigerators, shielded chambers that protect the qubits from the physical world. Inside these chambers, the temperature is kept at absolute 0. This level of cold is necessary to achieve the atomic stillness required for the qubits to function. These machines are being developed for specific high-complexity tasks, simulating molecular chemistry for new drugs, optimizing energy grids, and cracking advanced encryption. These machines function as specialized instruments for calculating the behavior of molecules and atoms, a task that lies beyond the reach of the digital computer.